Are you mathematical expert?
No, I'm not. I'm just using.
I'm trying to do figures.
ChatGPT is expert in mathematics.
What?
Well, from mathematics.
Plotting bank functions.
ChatGPT knows what to do with all figures.
No, I didn't know. What a great idea.
So, last several days, I draw very nice graphical abstract for my baby.
I mean, in bunch of
ChatGPT and mathematics.
I mean, ChatGPT, I mean.
You just ask, I need to draw this like in a nice way, and then it helps you a lot.
You pay for ChatGPT?
No.
Oh.
Too much.
Usually it allows me to ask enough questions a day, so
Yes,
I shouldn't pay for
I
this.
already used it today for.
So now,
Yes,
again, this pointer back, forward.
yes.
You can try it, please.
No, because we were using like.
Sometimes you need to click on touchpad there to activate.
It's a USB.
No, this is like
Not this.
different. Okay, but at least it's like.
Where is
TV.
Alex?
He didn't come.
Is it possible to like big this make this like bigger?
No.
Oh, okay.
There was also John 1 and John 1.
Oh no.
He has a net.
Yeah, and
And this is not connected. So
Okay, anyway, we should start this.
listen here because
You have-
yeah, I will
One
tell you. That's why I am
perspective
not
and
on.
That is not what I'm paid for, so I can just drink here. Okay, so let's start.
yes,
Okay, good afternoon, PCS members and friends. Today we are having a scientific seminar, but by Dr. Olga Bahrova. And our scientific host today is Dr. Sergey Konyakhin, who will introduce our today's speaker. Please, Sergey.
Okay, very nice to have you and to see you this near the Christmas day. I am sure everyone knows Olga Bahrova and so what happened to her before and during PCS, but then after PCS she has gone to Clermont-Ferrand, where she is now working with Dmitry Solnoshkov and Guillaume Alpesh on many topics of quantum optics, including the exciton polaritons. And this talk is on this particular subject. So let us welcome our speaker.
That was brief. Good afternoon.
Could you please close that stuff?
Indeed. Thank you very much. For
Maybe even, completely, because someone can try to go there.
Wow, the broad community, very interested. Thank you very much for coming, for joining me today. It's indeed a pleasure to come again here and to give a talk. As you can see, I will talk about exciton polaritons and mostly about topic of which you could see on the slides is directional polariton propagation in perovskite microcavities. And here I should stress that is a strongly birefringent perovskite microcavities. So as it was said,
I think it all requires introduction. I hope you will.
Yes.
Birefringent and perovskite and so on.
Yeah, what is directional propagational?
Thank you very much. Thank you very much for this. It's only first. So indeed, I will talk about all this. So what else I should say on this slide? That indeed I'm working on theory side with Dmitry Solnoshkov and Guillaume Alpesh. And the experiment on this topic was done in a group of ESU in Nanyang University in Singapore. And hopefully we will see this work this year appear on arXiv. So before we start, I shall indeed a couple of words about locations. So here we are in PCS, IBS, in Daejeon, in the middle, in the heart of Daejeon, in South Korea. And 9,000 kilometers away is a France, and here is a Paris, and around 4 hours by car or train, it's a small city of Clermont-Ferrand, where our Institute of Pascal, which is shown here, is located.
No, it's similar to IBS actually. Folklore, you know, the square shape.
No outline. So indeed, I am going to give like a very broad introduction, starting from planar microcavities, spin orbit couplings, well, some introduction on usual optical spin Hall effect. Then, and somewhere here, I will say a couple of words on intrinsic non-hermeticity, which appears here. Probably there is no German here, and what could be interesting and very interesting in this 2x2 matrices in non-Hermitian Hamiltonians. I mean,
but you are driving dissipator from the very beginning. It's always non-Hermitian. Yeah.
No, I mean,
Right?
in a non-Hermitian, in a sense, you know. Okay, I will talk about
Okay.
it. To jump, of course, I need to introduce polariton condensation, and then we are moving to main part of polariton propagation in cesium lead bromide perovskite microcavity. I mean, we will say about setups, what is the main effects which appear. Then I will conclude, and after all this, if we will have time, I mean, we show something more about exciton polaritons. Depends on how we will be running on time. And here you could see a nice picture of propagation from a point-like source, which should serve like a bridge. Bridge between what? So, to my understanding, one of the last seminar, at least last of the seminar of polaritons, one was on the focusing of polariton beam due to concave profile, the seminar about concave profile of the introduced by excitonic reservoir. Here, basically, I am also going to speak about some kind of negative refractive index, which occurs due to profile of dispersion, not some introduced, but some excitonic reservoir, but some kind of intrinsic one. Okay, then introduction. So we are studying indeed in exciton polaritons, planar microcavities. I guess for those people, I really no need to really go deep into introduce this. So yes, we are speaking about our favorite planar microcavities, where photons are, wave vector of the photons are quantized along z direction perpendicular to microcavities, and photon with some effective mass, which is non-zero, can freely propagate in the x-y direction in the cavity. And of course, it could couple with excitons from the quantum well and form our quasi-particles, exciton polaritons, which dispersion lower polariton are shown here on the right. And yes, we should highlight that our exciton polaritons are actually interacting photons, which basically gain some interaction from the excitonic part, but still have very low mass, effective mass, because it's a kind of photons. And in the very nice mean field approximation, we could introduce mean field by function for polaritons and write down Gauss-Pitayevsky equation with driving dissipative Pitayevsky equation. So, okay.
So you will consider resonant pumping, or it's just as an example?
This is here it's just an example, but indeed I will talk about the resonant pumping.
Okay.
I mean, the main part.
Yeah, because we usually discuss here non-resonant, so that's a big difference, I think.
Just two simple clarifications.
Yes.
Resonant pumping with in resonance with what?
Excitonic energy?
So omega p is the excitonic energy?
Somewhere close, right?
No, I mean in the same resonance in the sense that we directly inject we create polaritons with a peculiar frequency of energy. I'm saying there's no like stimulated scattering from the reservoir or current of condensate, and this is this sense.
This omega p lies within the dispersion of polaritons. So we can pick up any point in a polariton branch, lower polariton branch, and resonantly address this energy, and we can have non-resonant excitation with a very different case where the particles are stimulated, are scattered in stimulated manner to.
So this non-resonant one is the one where you excite them to a higher state and then the decay is.
Yes, and this is they behave like a laser. So they have some polariton state, and one can this hot exciton can annihilate and emit to this condensate state like a laser. But here we directly drive at some frequency with this within lower polariton range.
I see. Okay, so
Yes, very nice.
Because the loss comes with a purely imaginary term, right? Or gamma, is gamma real, or what is the
Gamma is real. I mean,
Gamma is real.
losses they are imaginary.
okay, and so the last term is then complex, right? Because of the complex exponential. But I would expect the pumping to be also purely imaginary, like the loss. Why is it complex like that?
In case of resonant pump, in case of non-resonant pumping, it would be imaginary.
Okay.
But this is like a driving force for the pendulum. It has all phases.
I see. Okay.
Okay. Straightforward.
Okay.
Well, okay. So here we are.
I may also add something for Annika. So in some experiments, I think, and in some of studies also by Sergey, you can even tune frequency of your condensate with your resonant pumping. So phase can be transferred from your laser to your polaritons using resonant pumping.
This is all of these experiments where they were with Anton Nolita was also maybe talking about, where they were looking at No,
these kind of experiments are non-resonant pumping, and these profiles they form spontaneously like snake instability for solitons in quantum physics. It's all more or less the same fairy tale.
Okay.
I hope that the speaker support this active discussion.
Yes, for sure. Yes, still, I mean.
It's not a first slide.
Yes, I mean, but it's a first slide. I mean, I didn't even think about. Okay, well, anyway, so we're going further actually, and since each basically because of the properties of the materials which we are putting inside the microcavity, this quantum well, actually each mode is basically polarization doublet, and we could speak different materials. Possess some different properties, so we could obtain different types of polarization splitting. Here, observe the spin splitting. So the most kind of known is transverse reactance transverse magnetic splitting, linear birefringence, which also, all this occurs, for example, linear birefringence occurs from from the kind of properties of material. So it depends how we grow the crystal from the crystallographic point of view. Also, there is a Raspberry-House spin-orbit coupling and some effective magnetic fields like the Zeeman split.
What is polarization? Linear? As far as we're, and sigma is Pauli matrix.
Yes, that's
Minor,
my
what is that?
next sentence, which I'm going to say. Yes, that's a good question. I mean, that's a good remark because yes, here I'm speaking in the basis of circular polarization
So this is
basis.
a circle.
Yes.
But this
We could make a transformation. I mean, rotation and go to another basis. It's just like usual stuff. So indeed,
So what does
No,
the,
1 minute, I know.
what does the matrix represent there? Is it the, so you have a sort of Hamiltonian, right?
yes. Okay, yes. Since we have some for each wave function site, which was on the previous slide for Gross-Pitayevsky, with a in this becomes a spinor, septospinor, and for each spinor we could write Hamiltonian, like 2 by 2 Hamiltonian, and each 2 by 2 Hamiltonian can, this can be decomposed over Pauli matrices, and I mean this omega, which could be like effective field which occurs here.
So all these terms you write are for polaritons now, not for photons or electrons.
Well, here it's a kind of linear regime, and we are speaking mostly about like photons. But since usually, what if we introduce like in a two oscillator model some excitons, like exciton resonance, it do not really bring from the term of topology anything new. I mean, so in some approximation, we could, to try to understand some effects for which come from photonic parts, we could use approximation just use 2 by 2 Hamiltonians. That's,
Yeah, but because my question is actually that Rashba-Dresselhaus, it's for electrons and holes and not for photons, I think. Or there are some analogs of this.
Yes, for sure. That's I mean, that's not that Dresselhaus. Again, that's just it call it because it has this shape.
You mean in the K space and sigma space, it's just the same as Rashba term for.
And that is why.
For semiconductors, okay.
Yes, for sure.
Okay, we'll go back to the earlier slide once.
Yes.
So where does that Hamiltonian appear in that delta term, like the first term in your Gross-Pitayevsky equation?
Yes, for sure. Here is the kinetic energy.
So yeah,
Potential. We are considering linear regime, so no interactions. Here is the losses, but on that slide there is no losses for now. And well, pumping will be introduced, like stationary.
I see. So you are just writing like a simple Schrodinger equation, but now with losses and pumping, and your Hamiltonian is this 2 by 2 Hamiltonian.
Yes, but it's become kind of a bit different. I mean, in a sense, different approaches. In a sense that here we are interested really in the dynamics, but here I mean we are interested more like in stationary Schrodinger equation. Also more like.
But you still have the pumping and dissipation, right? Or you don't even have that.
Here there is no that such kind of term. This kind of state of our so we could imprint by initial condition, some, for example, polarization or some number of particles or whatever we're looking. For example, I mean, we could solve, for example, so we are speaking about 2 by 2 Hamiltonian, so of course we could write down like a Bloch equation for pseudospin. And what is pseudospin here? I wanted to say, of course, and that is what we will be discussing a lot, I hope, during the next parts. Well, pseudospin or Stokes vector here is an average of values of Pauli matrices, and could be defined so the intensity as a degree of polarization, like S1 for degree of linear polarization, and S2 for degree of diagonal and antidiagonal polarization, and S3 degree of circular polarization. And all this could be, I mean, since it's 2 by 2, the simple dynamics could be visualized on the block, or better to say here, Poincare sphere. So if on the poles we have circular polarization, and the all linear polarization lies on the equator or in the plane.
So before maybe we proceed, this is a question to all of you, and especially to Sergey and Oleg, which is that so here we are talking about like a two-component thing coming because of refractive index.
Yes.
Now,
So for example, yes.
so now my question is, can similar thing be done with two spots?
Yes, it seems that kind of with 4 components.
Why 4? Why not? Because one spot gives 2 components.
Yes, one spot here in this approach will give 2 components.
No, in this approach, but I'm not talking about this approach. So forget about the refractive index, just have 2 spots. Can we try to reproduce similar physics with 2 spots, just with 2 spots and without any refractive index, for instance?
And maybe omitting the wave reactor dependence, of course, because this Hamiltonian strictly depends on the wave reactor, like it is shown in the distortion.
I think you can tune things to get the 2x2 linear path of your 2-spot problem to be exactly like this, but the physical meaning is obscure until you really want to create some particular matrix and think about what should you do to do this particular matrix in real system. So
Okay,
connection is not obvious at least.
but this mathematically can be done.
2x2 matrices are probably all equivalent something.
No, any by 2 matrix can be expanded.
Unless you
and
have particular
calculated.
symmetries can
Yeah.
protect you, of course, from doing something, but in
But here also there is no symmetry protecting anything.
yeah, then you can do whatever you want probably.
Any 2x2 system can be expanded like that.
So it's just a mathematical.
Yes, for sure. This is kind of playground. So what else I should say? Really, as was pointed by Sergey, here is 2 cross section for the band structure. Band structure in the case of the presence of TM splitting. So we have 2 different effective and effective masses for T and T, basically TM band. And if we to this, if we add some linear wave region, and that's what actually I will be talking hopefully in the main part, the cross section of the dispersion becomes like this. So here is along ky, like here there is some shift caused by BF regions, but on the kx we have some crossing which corresponds to occurrence of a tilted Dirac point. In this direction.
So could you repeat what will be the difference for x and for y directions of wave vector?
Here, you see here is the left part corresponds to ky, and the right part corresponds to Ks. Yes, it's not like here, but more. So yes, there will be some 3D plots of the dispersion.
So in fact, the plot was like an angle, but then you overlap.
Yes, I mean you just there is a ky, here is a kx. So it is a kind of the main point of all this talk is the appearance, because of linear wave regions and TM splitting, appearance of these tilted Dirac points here. So, and if we look,
and the dispersion is symmetric with respect to parity.
Yes. So basically, if we are looking, I don't show it, but if we are looking like from the top, we see just we have like here we just have like 2 circles with a different mass, and here it corresponds that these 2 circles are shifted.
You can also draw
You can draw the border. That's what I.
But I guess it's more.
How are they shifted on them? Could you please read it because I cannot
I mean,
hear?
No, I will show that.
Ah, you can show it next,
I
okay?
mean, not on the next slide, but on.
Sometime, okay.
So we can wait.
No, but
I agree with Bob. We can wait.
Yeah. It's hard to draw a circle. Okay.
So you're drawing some easy energetical surfaces,
Yes.
right? Okay.
So let's say, well, we should like look, and so this is kx, KY. And so this is the cut. Well, this is like very far above this cut. Well, but since here is will be our dear points, which we are looking for. Well, okay, that is some. Then I wanted to introduce some very old known results, typical for TATM splitting. Here is Hamiltonian 2 by 2 again, with inclusion of this TATM splitting here. Here is again this cross sections. So here I'm writing the component of the effective field. And that's why we was introducing this Planck sphere now to plot on this sphere this effective field by arrows. Since this effective field lies in the xy plane, like here, so I mean it's act in the plane. There is no SZ component. And here some so-called like. I guess extrinsic optical spin Hall effect was predicted some time ago in 2005, and then observed in 2007, and was kind of observed and like in the beginning of this year. So what we are speaking about? So we are. Let's say we have initially linear polarization for our pseudospin. So our pseudospin, let's say, lies in this direction of the sphere, like we will draw our here. And then because of the spin precession, I mean, this effective field acts it's visible from the Bloch equation. There is some precession of this pseudospin, and this precession results to the occurrence of different circular polarization components. And this is shown on this picture. So this is in experiment what was going on. They shine a laser with peculiar wave vector, introducing a polariton with a peculiar wave vector. And after in the time there is on a scattering and disorder, and in the results of scattering, polariton in a reciprocal space. Intensity, I mean, polariton become a distribution along the elastic circle, and here is S3 polarization in the experimental prediction and theory in momentum space. So it's a KY-KX, KY-KX, and so indeed we hear like fourfold pattern, which is also observed in real space. And again, it is seen from this picture, because, for example, if we have our pseudospin directed in this direction, there is in time rotation because of the field of this pseudospin in like here in one direction and here is in opposite direction, and our pseudospin becomes this component of the pseudospin in that direction, and since that direction corresponds to like some component of circular polarization, so S3 component appears here. And here is the same.
And what is the difference? You say the same, but still, what is the difference? So they managed to have natural materials?
Well, as far as to my understanding, they just produced more clearly this, these results, and probably here is something like bigger temperature. Well, I'm not sure that I remember this correctly, but at least here maybe it's like really high temperature. And
And what is the color there in this?
yes, color here is a degree of circular polarization, S3.
And they start with linear polarization.
Yes, I mean, yes, is linear polarization. That's a point actually over here.
And because of the spin precision, you end up with a SZ component.
Yes. Yes.
And why is this Hall effect? So there is some sort of quantization going on?
Well, for sure, I guess it is because of we are kind of gaining some. So because we could name this like effective field, and I mean.
So, I mean, what I'm asking, I guess, is that one can define some sort of winding number or something.
Yes, here there is winding number.
But is it like, you know, is it conserved or meaning is it always integer or is it?
Yes,
It's not quantum, I believe, Aniket. There's no word quantum home. It's
Yes, and
This is just like you calculate something and it gives you some function, something else function.
it's very classical. I believe.
I mean, it's a, you know, there is a zoom of this spin Hall effect, optical spin Hall effect. So.
Do these pictures depend on time? So if
Yes.
we let the system evolve for longer time, we will let the precision for higher time, and we will see another pattern of polarizations.
Well, ideally, yes, if there's no dissipation, you know, indeed there is oscillation, you know, indeed oscillation of polarization, and that is kind of is different what.
The time oscillation.
Yes, so I'm plotting this arrow here, so we start, and there is kind of oscillation there. I mean, kind of, okay, well, anyway, so yes, you are right. There is kind of. So this kind of was very something very quite old. Then something more new, another kind of view on optical spin Hall effect. And here it is indeed, there is no time, I mean, there's no time dependence, there is a kind of oscillation like, okay, and in space, that's it. In space, so it's kind of different type of oscillation, but still we could call it optical spin Hall effect. So again, we have TATM splitting, effective field which lies in a plane, and here, then we could introduce quasi-resonant pump and excite. So how is it excitation is going? So we have a very small spot in real space, which like very narrow, which corresponds to the very broad excitation and momentum space. So we excite all Asian states on some isoenergy, excite all in the energy curve, and excite with some linear polarization. And this also leads to occurrence of some oscillation now in space. And again, there is appearance of S3 component like it is shown here. And there is some oscillation in S1 component.
Sorry, before you move on, what is, could you explain this psi plus minus, chi plus minus, what are those things?
Ah, yes. So it's again this, I mean, this is a variety.
Psi plus minus are the two components from before, right?
Yes, and
But
here is the coupling with the Rabi splitting to the exciton. So chi is again exciton wave function, mean field wave function. Again, it is a spinal.
Chi is exciton and psi is photon? Or?
Yes.
No polariton anymore. Exciton and photon explicitly.
I mean,
but you can write.
I mean,
Okay.
here it's just.
So what you are saying is that you can write a similar Gross-Pitaevsky equation for just the photon part?
It's non-interacting, I think. Just linear.
Okay.
No, here is there is a reduction because interaction comes from exciton.
Okay, or only for excitons.
Yes, for sure, because now we are kind of decompose,
Okay.
and yes, we are looking, for example, all this splitting in photon part and interaction, like copolarization, and between polarizations are coming for excitons. Well, and here is, of course, our quasi-resonant pumping. Here is decay for photon, decay for exciton, some potential, if we want, let's say, and again, birefringence. Yes, here is birefringence and some TATMs. well, it's just more explicit form. So basically, we could, here, what I want to stress here.
Could you also point out how you model quasi-resonant pumping? Because I see a similar kind of term for pumping.
Yes, and here it
But
is.
why earlier you called it resonant pumping? What is it quasi-resonant?
Very good question. Well, let's call it resonant pumping.
Okay then.
No, okay, well, let's stop on this. So I want
The only difference that I see from earlier term.
there's no difference.
No, there is a difference. Here, P is a function of X and Y. Earlier, P was just a constant.
Yes, but this is encrypt real space profile of this pump.
So earlier also you could have a profile like that?
In that case it was homogeneous, and here, because I want to stress that we have a very narrow pump in real space, we are pumping actually somewhere in here, this very narrow pump, which allows us to excite the whole iso energy or iso frequency curve, like here. Yes, and here again, what I want to say again, that here again we have this fourfold pattern, but with some modification oscillation. So, well, a couple maybe of words that if we add some polariton interaction encrypted by this term, we have some, well, because this interaction in the terms of effective field can be viewed as appearance of nonlinear SZ term. And if this SZ term is quite big, we have like huge distribution of polarization intensities in real space, like here. But just my mark. Okay, probably we could move further. It's one of the grounds. Well, now was slide from John 1. Okay.
Sorry, please go back to the
Yes.
slide. So the direction of deformation of these figures is imposed by by which term in the equation for psi?
He sent the email.
Because you have explicitly written axis X and Y. So
yeah, well,
why not Y and X?
Sorry, could you repeat the question?
Why deformation of this pattern occurred, for example, as squeezing along y-axis but not x-axis? From which term in the equation? Favors the x-axis? Let's say.
Yeah, that's a very good question.
So you mean instead of fourfold symmetry, now you have only twofold symmetry?
Yeah, it means that in the equation we should have some symmetry breaking term, and I'm trying.
It's spontaneous.
So
No, here it's really, I should say that it's quite because you see why it happens, as I said, because when this term here, nonlinear term, which occurs for SZ from the interaction. So when, for example, it's quite big, so big corresponds to effective field like along x and then z. So with the time, spin starts to kind of be locked to some direction of direction of this SZ. So if we have this, yes, if we have some component, magnetic field is strong, so quite strong, and we have this pseudo-spin, let's say, initially again in this linear with a linear polarization, so it starts to precess, but it's like in time precess more and more and very close. Code very close to this interaction term as Z, so it's kind of start to be locked to this.
Maybe another more basic question is, do I understand correctly that the left two figures that you have, S1 and S3, there you don't have the second equation of chi, and the right one has the. So what term? So you wrote the right two figures appear when you add polariton interactions. So which term corresponds to polariton interactions in those two equations that you have written?
Yes, here is a.
The chi-square, not chi-square.
Yes, yes,
right?
yes. So it's a kind of column-like interaction. Yes, because chi is here outside of the bracket. So
Okay, those are accidental interactions, first of all.
Going back to my question, is the spontaneous symmetry breaking or this direction is imposed by linear polarization?
I guess it's imposed. Well,
I think if you just look at the full equation, then there is no fourfold symmetry, right?
Yeah, that's what one has to find out. Yes, no
I don't think there is the symmetry. I mean,
symmetry
with just
in exchanging x and y, you don't have.
yeah, I think if
symmetry.
you just have the two modes, psi plus and psi minus, maybe then there it is. But then when you introduce this interaction term, then it's just gone.
yes. I mean,
So
Right,
one
but-
of the terms is not symmetric under exchanging x and y. So which term is it?
you here, for example, we cannot exchange x, y, for example.
Yeah,
from
if you have a term like
Yeah, but
psi
here you
square,
still have it.
yeah, so
I
it's
mean,
not.
fourfold symmetry means that you have a symmetry in x to minus x, y to minus x, and exchange of x and y.
So this is some kind of internal symmetry
Yeah.
of the crystal.
yes, and that's what ST.
The moment you introduce interaction, then it's gone.
Yeah.
Because you have mod squared times that term. So then if you exchange x and y, as Barbara is saying, you won't have this much.
Yes. Okay, thank you very much. So, well, here is more provoking slide. So a lot of people are speaking about, I remember maybe even here, even now there is a talks on we write some 2x2 Hamiltonian and add some imaginary imaginary term, which usually Hamiltonian become imaginary. And all the agent vectors and agent states become imaginary. And so, there is some physical reason for this. Yes, here is one of the answer. So it could come from the line width anisotropy, as it is shown here, for example. So here we are, our Hamiltonian, let's say the same, and we introduce some imaginary term like this. Which corresponds to introducing of different lifetimes for two linear polarizations. And this is, visible like here, and there is some picture from experimental line width. So we could see for example, there is a really visible difference in line width here and here, for example. Here is kind of more broad. Yes, and this could result in appear, well, yes, and what else should I say? Here, so yes, if we have this here the TATM splitting and we, as I said, add linear birefringence, we could obtain appearance of some tilted Dirac points. And well, here is a bit similar. So if you have some Dirac points like this, so it's a zoom. And we add some term like this, anisotropy, imaginary, we could occurs, well, there is occurrence of two so-called exceptional points marked here in pink, and some so-called Fermi arc. Bulk Fermi arc in real space, again, this is imaginary part of the energy, so there is a Fermi arc imaginary. And these exceptional points visible again on the S3 polarization pattern, like here. This is very close. So here we have initially Dirac points, and then they split into two exceptional points with a different polarization, circular polarization. So it's a theoretical picture and experimental from experiment. Also, I should say that I did kind of a bit different non-homogeneity could lead to shaping of Dirac points into a ring of exceptional points, like it's introduced here, and check it out, for example. Also, there is some really big stories with this shaping of Dirac points, so and some braiding or annihilation of Dirac points, etc. So just let you know. Well, on this slide, I just wanted to say a couple of words on the creation of macroscopically occupied state, or in what follows, just say condensation. But I guess everyone is tired of seeing of this picture. I mean, seeing this condensation of polariton. So I just should say that because here we have like bosonic quasi-particles. So some macroscopically occupied states in condensation, equilibrium and non-equilibrium could occur here. And now let's move. To main part of this talk. So again, I'm highlighting that we have some experimental which was done in Singapore in group of issue and theory side from our group. So and now here is the setup. So it's a quite massive slide, which somehow not visualizing here properly. I don't know why. It's wrong with mark something.
On the monitor, it's also not very good. So
quality.
Well, probably it's because it was open this mark and from the Windows. I wanted to run it from my computer, but no way. Well, I'm sorry, but it was kind of a main slide. Well, so here we are, our perovskite microcavity. So we have some DBRs, this non-organic cesium lead bromide perovskite here, and some DBRs, another DBRs. And we shine, they shine a laser with a K0 wave vector, I just say, and see some propagation of polariton distribution. They are, yes, that is the point. They are shine non-resonantly, but because, again, they are this is the point. I'm very kind of interesting in some sense because yes, they are. That's why I was introducing non-resonant pumping, because they are doing non-resonant pumping scheme. However, because of they are shining as a very tiny spot, and basically they by changing the size of the spot, they are somehow can obtain condensation and different energies and different frequencies, like in a quasi-resonant pumping scheme. So, and that is the main point.
how condensation usually should be at the minimum of the spectrum?
Yes, and that's why I'm saying this is not like true condensate, Bose-Einstein condensate. This is kind of non-equilibrium condensate or lasing, people refer to polarizing lasing, or no, I mean, better to say non-equilibrium condensate.
Difference in blue shift, difference in momentum of this energy.
Maybe. Okay.
Well, but I'm doing some kind of creating non-equilibrium condensates. Yes, and here it should be some 3D.
The perovskite is ferroelectric. That's why you have all these funny terms with beta, right?
Yes, and one of the main points for this perovskite, which I wanted to say in a minute, that indeed here is a very strongly birefringent material. Well, and with some strong TATM splitting. So you could, hopefully you would be able to see that actually these birefringence, in contrast to, for example, our arsenide gallium microcavities, when this is kind of less than 1 mm or around 1 mm, here this birefringe like around almost 20 mm. That is kind of 10 times bigger.
And thickness of perovskite is just wavelength.
Well, somehow
So just all space between DBRs is filled with a perovskite. No some kind of other space, or so a perovskite is not like thin layer for quantum well.
Well, to my understanding is like perovskites is like arsenide gallium in our usual kind of.
Yes, but in typical semiconductor microstructures for polaritons, we have some filler material and quantum well material. So here it seems that everything in homogeneous knows some quantum well line structure. Is it true? Because I am not familiar with this technology.
Well, that's very good. Well, to my understanding, I mean, yes, no.
Okay.
Without quantum wells,
what is
Rabi splitting is very tiny if you don't have a quantum well, right? In the middle, you need to increase Rabi.
well, maybe I mean the.
Anyway.
No. Well, of course they are doing probably. No. That's not true because I mean, because there is some compounds of perovskite, like for arsenide gallium, there is some compounds from which we create this kind of periodic filling with a quantum well, and probably there is something here like this. Because
Principles
here,
are from perovskite.
yes, for sure. That's why I'm speaking about this perovskite.
Okay, but all this stuff is about optical properties, and excitonic properties is not optical properties.
Yes, but excitons here come just to distribution of mass. I mean, effective mass. So it's a shaping of the dispersion of the high wave vector. And here, yes, and indeed here the Rabi splitting is very huge. It's like 100 more than 100 mm.
Rabi splitting between what and what?
So here is a polariton dispersion, but you maybe remember from this slide. Yes, here is what this was dispersion, like photon, excitons, and here is the Rabi split.
Okay. So it's the distance between the minimum
It's
point?
like an anti-crossing point.
Okay.
This is a bizarre slide. Well, so the main point was that a huge TATM splitting and huge stone bear features, which results that again we have this appearance of the Dirac point. Okay, this is visible. So here is the photoluminescence intensity below threshold, and cut in the dispersion in which the tilted Dirac points occurs, which visible here.
TATM splitting are this given by this beta terms, right?
Yes.
And what is the term responsible for birefringence?
Yes, here it is.
This beta naught?
Yeah, it's proportional to sigma x.
Okay.
We just shift these parabolas in a vertical direction. So we could deduce its value from this splitting.
So the importance of this material, bromide material, is that it introduces birefringence?
Yes, and the big value of it.
Okay.
So around 10 times bigger than Jas and Gallium. And you see wave vectors and around 4 inverse micrometers at which Dirac points occurs. It's quite big values. Yes, so here is a dispersion below threshold with some theoretical fit for it. What we also, yes, I introduced this Hamiltonian, so is the agents vectors, agent energies for this simple Hamiltonian. Then we should introduce excitons, which appears to this 4x4 shaping of Hamiltonian, and this results. This is more important in the more exact fitting of the dispersion, because, for example, you see that here there is change, maybe not really, but there is changing in mass between these two branches. For example, here it's kind of more photonic than here. And this is resulting kind of some mass anisotropy along the wave on big wave vectors. Yes, and since I mean, in experiments they are able to achieve this condensation at different energies, and we do this with the resonant pumping scheme, of course. So there are kind of several regimes which could occur. So if you are looking on the either end frequency curves like this for this distortion, it should be this. I mean, ideally, here has a different regime. So here is I mean, somewhere Dirac points, and slightly above the Dirac points, we have kind of a hyperbolic type of the dispersion. Okay, it will be visible on the next slides. Then its result, if you move in energy, the shaping is different, so it becomes kind of flat, and then the parabolicity is restored. And this should kind of, maybe I should not pay attention to this, but this what is important here is that we are controlling the frequency of this beam of polaritons, and this is kind of the how we determine different regime for polariton propagation. And by I mean, what is called in the title directional polariton propagation, it would mean that for these different frequency curves, we have kind of different refractive index which corresponds to them, and this could result to focusing, for example, in the hyperbolic regime, or some collimation of our propagation in this direction at which Dirac points occurs. So maybe let's look on some better pictures. But before that, yes, I'm again introducing this. Well, here is Schrödinger equation, basically because of nonlinearities, and we are not treating the nonlinearities here because most of the effects come from the shaping of the dispersion, and because all this occurs in at the very huge kinetic energies, so like interaction is really not brings too much. So here we have a Gross-Petersky equation for photon and exciton mean-field wave function. Again, it's the same as on the previous slide, and so how we proceed with our calculation. So indeed, we are working in a quasi-resonant pumping scheme.
Sorry.
You told that it was non-resonant.
Yes, they are doing this non-resonant pumping.
But in simulations, you are doing it.
Yes. And that's what I mean. That is one of key points, because they you see with what we want to do, we want to precisely control that the energy of our current polaritons, and that's what we are doing simply with the resonant pumping. Yeah, and since we are creating some coherent condensate, and everything is fine. So I mean, in this sense, I mean, from numerical point of view, and from theoretical point of view, it's really easy in the kind of more controllable way, because for non-resonant pumping, it's we are not really controlling the energy of our condensate.
But maybe you could add some gain term in the momentum space to
yes, that's it.
make selectivity for wave vectors.
Yeah, it makes selectivity for wave vectors, not for the energies.
Yes.
And that is the point, because you see on this dispersion, we will open. So there could be like two optical spin Hall effect. Comes from oscillation between these two in energy, so this is the energy. This is the wave vector. Let's say the else. And if we are if we are targeting with the non-resonant pumping selectively some wave vectors, let's say somewhere here, we are kind of not obtaining. We are not exciting one is a frequency contour, like not even, we are exciting two energies precisely, and that's what we do not want this to happen. And we want to.
So in general, you have very hand-waving explanation, but too much experiment, we should do like this.
Well, this is because I mean, in experience, they obtain some Okay, I will show on the next slide.
But the question is how in experiments they can say that they excite polaritons with particular energy with non-resonant pumping. That I don't understand completely.
I guess it's again because it's like to my understanding, it's somehow similar to the resonant pumping scheme because they have like the dispersion, let's say. Say like photonic one. And yes, this is K energy. Okay. Yes. Or maybe I should draw like full. So if you excite very narrow in a, it's well again very narrow in a real space, that corresponds well in general. Narrow excitation in real space corresponds to the broad excitation in momentum space.
Okay.
And because again they somehow excite with a very narrow spot in a real space, they obtain condensate.
Anyway, how do they experimentally control which energy they want to excite?
Well, they are saying they are doing this because of changing of the pumping spot, like in resonant pumping scheme somehow.
So they are changing the size of spot and various energies are
Targeted. Yes.
yes. And in general, does the very simple reasoning work? So they have size of Gaussian spot, they have wave vector, and wave vector corresponds to at least some energy scale. And the excited energy is of the order of energy which is given by this simple relation. So we have size, we have wave vector.
Yes, yes.
From wave vector, we have energy. So of course, these are splitting, but still some energy scale. Okay, some medium maybe.
Well, I guess it works somehow because really the scale of all this stuff is quite big. I mean, in the sense that well, here we have like 20 MeV. You see, it's quite a big, and here we have wave vector of the order of like 1 inverse micrometer or even more, depends on the energy. But we will see from the bigger figures that indeed they are not doing it like condensate, which occurs really not really precise, like in a bit different distribution of intensity in a circle space comes from this non-resonant pumping. Well, but you see, this approach is working. We are creating condensate. I mean, the resulted condensate are the same. Well, so.
Okay, so it's 5 p.m. Let us, without interruption, let Olga finish her talk and then maybe discuss somewhere else.
Yes, because we are coming to the most.
Yeah, please.
And
please now without questions, I think.
Well, we could.
Okay, continue.
Yes, so that's because that really was very peculiar point. So yes, some bit of points on how we proceed this calculation. Yes, we do this resonant pumping scheme, narrow Gaussian spot, which allows us to excite either peculiar energy curves. We do this on the Gross-Pitayevsky calculation on the spatial mesh. With these numbers, we do this time integration by multi-step methods, and we use GPUs on this PyTorch using on cluster. So that's how calculation goes. And eventually the results. So first we start with the most interesting part, kind of flat. So again, all pictures are mess somehow. I'm disappointed. So we are moving on again. Here is the energy scale. We are moving. So somewhere here the Dirac points. We are in the flat regime. And now I will show why. So here is a dispersion cut below threshold. Here is in our case condensation. We have there is indeed condensation and some peculiar energy occurs. And here is luminescence from isoenergy contours. Well, so you see this, okay, this part, and with some theoretical fit. And we are zooming in this region where which corresponds to the location of the Dirac points, but I'm saying we are still kind of above the Dirac points. And we'll see this part quite flat. I mean, there is an isoenergy curve here. So a lot of particles propagate in the same direction with the same group velocity. I mean, just similarly oriented group velocities like here, depicted by arrows. And well, this result is that in the fact that in real space we have like very directed propagation of beam, like very localized or very canalized beam, and that's what we called canalization. Because, for example, in the opposite this ky direction, you see there is like a huge divergence of this beam, and here the beam is very kind of narrow in width. And again, this is zoomed picture, and this is the same zoomed picture from theory. Well, indeed, we have like a very directed propagation of polariton. And well, this is some formula in order to estimate the effective mass or curvature of this dispersion near the Dirac point. So there is some kind of isotropic or parabolic curvature, and due to presence of this splitting, we gain some additional terms which shapes our isofrequency curves. And yes, I'm here to say that indeed this is a gene where we have biggest collimation effect or bigger canalization effect. So, well, then on the next slide, we will move a little bit below in energy to the hyperbolic case. This again, polarization resolved PL below threshold and above threshold, where they obtain some condensates and some energy. This is either energy curve here. This is zoom one. This is kind of very interesting hyperbolic regime. So in the sense that here is quite this curvature is quite of a minus hyperbolic one. And so this corresponds to the fact, so we could see that a lot of particles have group velocity with this directed like inwards. So we should have some focusing effect. And we like focusing and then divergence, like usual concave lenses. And so here again is a cut of in real space of this beam. We should see there is slight divergence, and then bits of the beam is quite big. And this is the same for simulation. Well, here I should say that there is slight divergence of polariton beams here. I mean, and overall broad. And of course, I should mention some proving of condensation, kind of non-equilibrium condensation, or creation of macroscopic light state, better to say. So there is a S shape of intensity, like here in red. There is line width drop up to 2 MeV in blue, and there is some blue shift around 8 MeV. 8 MeV is a huge value of blue shift in respect, for example, for gallium arsenide microcavities, where it's like 1 MeV or even less. So because here is everything is on the large scale, and this is shift also quite big. Then we are moving to another kind of more above in energy and go to the parabolic regime. Again, the same photoluminescence polarization resolved in below threshold, above threshold intensity in reciprocal space. And here is energy with the frequency curves. We again zoom in, and see that this is kind of parabolic curve. So there is a divergence in the propagation. And it is visible on this real space plot. And in the theory or in experimental and in theory. However, we should say, yes, indeed, there is a huge divergence, but there is still some directionality in this propagation, because if we look, for example, in propagation in other direction, ky, and look somewhere here, and zoom, here is this cut, and then here is a real space cut, and see that indeed this is kind of much more divergent, this beam, if you even say this is a beam somehow, than, for example, this one. And this regime is called like arc-shaped regime because it's like a mountain up. And so we are saying that in all this regime, direction of the group velocity based on the shaping of the dispersion dictates diversion of polariton propagation. Then to be more quantitative, we should say, well, how we could estimate this divergence. And well, let's do it. For example, let's take the width of this beam for each x point, and for each x point along, for each x points, so in the x direction. So we're kind of fitting it with some, let's say, Lorentzian in the y direction, and extract some widths and blah blah, and plot it for different regimes. Here is again we started with this arc-shaped, so the huge divergence and huge value of the widths, then parabolic one, a bit less of divergence, then hyperbolic with some diversion, and then most coordinated or normalized flat regime. In that, well, okay, then we could extract a slope for these curves and plot the slope versus energy, and normalized on the like less collimated case, and see in how much time this flat regime, for example, less divergent than arc-shaped. And then, yes, the answer is more than 20 times. So this red points corresponds to different experimental data and different experimental regimes. And of course, black one corresponds to some theory values which were extracted from theoretical calculation. Well, that's how it is. And the last point which I want to say is, so we can move in energy. So why we are not directly exciting Dirac points? Why not? If we could do this, why not? So yes, we are doing this, and what we are getting, so here is a theory and experimental picture. So starting from the polarization intensities. So here is one polarization intensity in which we could observe pattern some modulations along the y direction, and well, okay, some so-called stripes, and but still we obtain some fourfold pattern. So okay, better to say butterfly pattern, which is visible in experiment. Then we are looking, yes, and by the way, here is a full intensity from experiment, where we also see some kind of firstly butterfly-like pattern, and secondly some modulations along this direction. And then we are looking on the polarization degree, that Stokes vector somewhere. So here is theory, experiment. So linear polarization degree here. We have some, okay, again, modulation in this direction, stripes, some a bit of modulation and fourfold pattern in degree of diagonal polarization, and clear stripes in S3 or degree of circular polarization. So what we should say from this? Of course, first that indeed there is some kind of butterfly or fourfold pattern which could be restored in general, which somehow reminds us optical spin Hall effect, which we discussed previously. And then there is some modulation. And if we are looking on some modulation, we are having in mind, oh, maybe there is some interference going on here. So indeed, it is. Again, so for this, we should look on the in the momentum space. So here is an energy curves on the energy of Dirac points. So here is the Dirac points crossing, and here is experimental picture for the intensity. And so, if you look, what we could see from this, if you are looking in this direction, well, kx direction here, we should say that there is some kind of 2 points in which our group velocity is directed in like group velocity directed perpendicular to the contour, directed in this direction. And if we are exciting them, well, actually, so this could lead to some interference between this with these 2 points. Well, and there is some period which determines by the wave vector, depicted here, k star, the differences between these 2 k vectors. And indeed, we are looking at this calculating this wave vector value, which is like this, and then we convert it again in the period in real space, which will be 2.5 micrometers. And indeed, here is a period of these stripes, and it's 2.5 micrometers. Okay, well, and this is somehow well, some reshaping of the original spin-fold effect because of the properties of the dispersion. Well, and so, yes, here I'm saying that indeed this stripe phase is the result of interference between these 2 points. Well, again, and we are coming to some conclusions. So, yes, first shaping the frequency or energy of our beams, shaping the dispersion, we could obtain some, let's say, optically configurable canalization of exciton polariton condensate in our birefringent microcavity. So again, I remind here some several regime of directional polariton propagation which occurs here, like hyperbolic, flat, parabolic. Well, then we calculate and observe that there is canalization with a collimation factor for the flat isofrequency curves, which kind of reaches to 20 times, more than 20 times. Well, and second, if we directly outside the Dirac points, this spin-orbit complex result in a shaping of original optical speedhole pattern in those stripes. This is a periodic modulation of intensity and in polarization components. Well, that is. Thank you very much for your attention. Merry Christmas. That is done in 10 minutes.
Maybe some brief questions, and I have one actually. By using my power, I can ask. So you shown theoretical calculations which are really very nice stripes. Could you go back one slide, maybe or two? Mm-hmm. But here experimentally, you clearly see that some checkerboard pattern occurs for S3, for instance. I mean that there is some red, blue experimental pattern, which is clearly see why it's there is some. I cannot see a big agreement with the theoretical one. What is the difference? What is the origin of this discrepancy?
Okay. Yes, the answer is simple. Theory is a kind of theory. I mean, it's somehow perfectorized. So indeed, we have like a perfect distribution, and well, you see, this originates from that four-fold pattern. Because, for example, here you have red, blue, cross pattern. Okay. And this kind of from original spin-hole somehow. And here again, we should see this, and we are really, yes, I agree that we are not really seeing this. Clearly, this stripes pattern. Yes. That is again because firstly, I guess this is because if they pumped, for example, really resonantly and excite properly the engine states, or okay, let's say in the iso frequency curve, then they would get some more precise stripes. This is the first one. Second one, of course, because then for sure, maybe there is not fully linear polarization in experiment. Because we are pumping with a peculiar one linear polarization. And here, because there is also some rotation of the sample, for example, which really here is, and this results, for example, in some in appearance. So the linear polarization determined not like 100% right.
Okay, so experiment is not perfect. Maybe
I can ask.
one brief question, yeah, Nikat, please, and then
So-
we'll close.
You mentioned that in what you want in theory at least, you want to select an iso energy contour, right? How do you do that in your equation? Because in your equation, if I remember, you are again selecting one wave vector, or how are you selecting one frequency? Yeah.
Yes, I mean it is. Yeah, I know. Yes, because we are selecting one frequency. And this plus minus corresponds to we are choosing like polarization, which we are want to with which we are want to pump.
Could you maybe just show the very first slide with the Gross-Perovskite equation with resonant pumping once again?
Here it is. I mean.
No, the very first one.
I mean, it is the same.
Is the same?
Yes.
But then,
Because here it's just written for spinor, and here I mean just separated photon and exciton, but basically the structure is the same.
I see. Because what I then understood, maybe then I don't understand, because in that picture that you were drawing there, that if you choose resonant pumping, then you are choosing one wave vector.
No.
And as a result, you are choosing two energy contours, and you didn't want that in your simulation. And that's why you changed your simulation in some way. Did I understand this correctly?
You understand correctly, but you should replace first word should be like non-resonant pumping scheme.
Oh, okay.
That's what we are pumping in resonant pumping scheme.
I see. So whenever you choose resonant pumping scheme, you are choosing one.
Yes. So we are choosing one energy.
So Sergey should say this. Let's say the speaker again.
Okay, let's say the speaker again.